morning, everyone. So as the title of my department might not suggest, I'm in charge at Pasqal of the development of analog and hybrid quantum algorithms. So today I'm happy to have the opportunity to talk to you about Pasqal and about the development of applications on our neutral atom platform that are being run today. So in the next 15 minutes or so, I'd like to cover the following topics with you. I'll first give you a brief overview of Pasqal history and of the history of the neutral atom technology that is powering our computers. I'll then tell you how we are turning this academic excellence into industrial-grade devices. I'll then explain to you how we are partnering with academic and industry leaders in the development of quantum solutions to their use cases. And finally, I'll show you how we are turning these algorithms into reality by actually implementing them on our quantum hardware today. So let's start with Pasqal. So Pasqal was created 5 years ago in 2019 by a group of people that includes our CEO, Georges-Olivier Raymond, Alain Aspect, who ended up getting the Nobel Prize in Physics a couple of years later, and Antoine Brouwys, who's been spearheading the field of neutral atom technologies since the very beginning. Pasqal has now grown into an organization of more than 200 scientists and engineers, and we've been partnering with a bit more than 30 clients with which we are developing actual applications for their use cases. And 10 of these are currently being running on our, 10 and more of these are being running on our devices. So we are building upon 4 decades of academic excellence from our co-founders and their colleagues. The last 15 years have seen the neutral atom technology rising into one of the major platforms for quantum computing. From the early experiments involving only a few atoms to the latest developments where people are now able to control hundreds of them, the field of neutral atom is ready to leave the academic labs and enter the industry. But turning such an academic experiment into an industry-grade device requires very careful engineering. The end user will be expecting to get steady access to our computers. So this means we need to increase accessibility. So this first can be done by increasing the reliability of each device individually, by increasing their uptime and repeatability. But this also means that we need to be able to provide more devices to users. And to that, we need to increase the reproducibility across all of our devices and reduce the time it takes us to build them. So with this in mind, we now have 2 R&D devices up and running, focusing on 2 main tracks, increasing the number of qubits and building the base for the future FTQC program on neutral atom computers. We also have one engineering. There's an issue with. So we also have one one industry-grade device that is up and running, available on Now Cloud and also on Azure Quantum. And we have two more devices on the way to be delivered later this year into HPC centers in France and Germany. So in order to achieve this, we are using a modular approach to engineering. The goal here is to mutualize the efforts that our colleagues are put into the development of each of our devices. The idea is that any new feature would be created in the form of a new submodule. And then this module can be easily incorporated and integrated in any of our devices thanks to a shared set of interfaces. As an example, we've developed an optomechanical bench here, this small block here that you see on the right, that is designed to control our qubits in space. So this module was created with fixed specs and frozen capabilities. This means that it's intrinsically more stable, and it's way easier to integrate and to bring to new devices. But having the best hardware while being necessary is definitely not enough to get people to use your quantum computers. You need to be able to provide algorithms and applications for people to use. So that's why we are nurturing a very vivid ecosystem involving people going from cloud providers, software developers, and end users. And through these collaborations, we're able to build applications that are of relevance to them. How does it work in practice? So we are actively collaborating with potential end users, with actors of various fields. So this makes sure that the solutions we are developing are relevant, both from a technical point of view, as well as an operational point of view. This means that we want to make sure that once the technology becomes mature enough, it won't take too long for it to be brought to applications. And because of our devices are already operational, we are focusing right now in the development of algorithms that are readily implementable. This means that we are focusing, at least at the moment, on analog algorithms and hybrid algorithms. These can be applied to a wide range of applications and are readily implementable. And because of that, those algorithms are running now, and we are now able to start benchmarking them, providing very useful insight into their potential and into how they could be later turned into industrial usage. Here, I present to you a couple of selected use cases that have been run in the last few months, and I will now walk you through a few of them. So let's start with a couple examples coming from physics. So here I have two use cases that were run with academic partners. The first one on the left is about optimal control of our devices in the goal of preparing a specific quantum state. This quantum state is related to an optimization problem, but here let's just focus on the state preparation itself. The one on the right is really about theoretical physics. It's about the so-called PXP model, and it's about studying the dynamics of this model and do some prediction about its behavior. So here, in those two examples, the problem sizes were still small enough that they are manageable by classical means, but the key message is that if you compare what we expect the quantum device to produce and what the quantum device actually produces, you find very good agreement between the two. So this means that the devices are behaving exactly as we expect, and once we reach sizes that go beyond the capability of classical, we can actually trust what the computers what the quantum computers are giving. If I now go to a different set of applications, so let's go to quantum chemistry and drug discovery in particular. On the left side, you have a use case of toxicity screening. The goal here is to predict, given the structure of a molecule, whether they will be toxic or not. So to this end, we've developed a proprietary algorithm relying on classical machine learning methods and a bit of quantum computers in it. We're able to test on a data set of 200 graphs and try and predict the toxicity of molecules. We were able to show that our method is on par on this data set with classical methods, and we were also able to prove that, to provide an artificial data set on which it was really surpassing significantly the results. So I'm sorry, there's a bit of an issue with the display. Yeah. On the right side, we have another drug discovery-related algorithm. So it's a hybrid application that we've developed in collaboration with Qubit Pharmaceuticals. Here, it's all about molecular dynamics and about trying to compute the interaction between a molecule and the proteins inside of our body. So here, one of the key questions in molecular dynamics and in these studies is what is the effect of the water molecules that are there in between the protein and the drug. And we've developed with Qubit Pharmaceutical a way to turn the question of locating the water molecules into an optimization problem that is particularly well structured and particularly fit to be implemented on our neutral atom computers. So these we ran last year in our machines, and this led to this scientific publication below. And let me give you a final set of use cases that we've run, and then this will allow me to put the emphasis on how hybridization of classical and quantum is extremely useful. And this starts from now with our current devices. On the left side, it's an optimization problem that we implemented with the help of Credit Agricole and multiverse computing. Here, the original use case is about credit score rating, or the so-called fallen angels, which are assets whose credit rating drops below investment grade. And the goal is to try and predict early enough that an asset will become a fallen angel. So the way we solve this is by combining machine learning method to try and classify and predict which of the assets will become fallen angels, and combine it with a quantum computer to increase or to improve the classical machine learning framework. And what we showed, what we obtained, is that by using the quantum computer, we were able to reduce significantly the size of the machine learning model that was solved and that was used to answer the question. So this showed that by combining state-of-the-art classical methods like this machine learning approach and the potential of quantum computers today, we can really get something very meaningful and in a very short term. And the last use case I want to mention here, I'll be extremely brief about it, is a use case coming from telecommunication, where here the goal is to assign identifier to cell phones, and with some constraints about nearby cell phones having to have different identifiers. At the end of the day, this question of assignment of identifier turns out to be, in algorithmic terms, a graph coloring problem, and this is one that was solved with people from Links Foundation and Shineka in a hybrid manner, where they used state-of-the-art operation research method called branch and bound, and combined it with quantum elements to make it a bit faster. So if you want to know more about this specific use case, please come back in this room later today, when my colleague Mourad Beji will be presenting it in more details. As the last remark, I'd like to come back to give a few words to you about the full stack approach of Pasqal. So we are working across the entire pipeline from the very bottom and the hardware consideration all the way to the top and the user's interface. And one thing that is extremely important and that I want you to get from me today is we need to get people to engage in the development of solutions, because we believe that the first relevant quantum applications will come from very dedicated, very specific applications developed in collaboration with the experts of the classical world. And to this end, we are now providing no-code interfaces and a quantum learning platform to help engage people and train them into our technology, and thus improving and speeding up the co-development of solutions. So with this, let me just recap and give you the take-home message for today. We now have at Pasqal industrialized QPUs, namely we've turned the academic experiments into reliable devices. We are developing solutions in collaborations with actors in the industry, and those solutions are being implemented today on our devices. And let me advertise, let me give you a bit of advertisement for today. So if you want to know more about Pasqal, please join us next week when for this webinar, when we'll be unveiling our roadmap. You'll get to know more about what we're going to do in the next few years. And with that, I'll thank you and welcome your questions.
Okay, thank you. So we do have a question or two. First, there was a question about the approach for the toxicity prediction use case. Question is, was this gate-based, variational algorithm, or reservoir computing?
The
toxicity prediction.
The toxicity prediction, the use case was, there are data sets of known molecules that have been tested to be toxic or not. And the way we were encoding this is we are encoding the structure of the molecule, the geometric structure of the molecule, into a quantum computer. And then by looking at the dynamics of the qubits in the computer, we are extracting characteristic features of the structure of the molecule, and we're able to show that there are key elements there that are easy to capture by quantum dynamics and that are harder to capture from classical means. I hope this answers the question.
I hope so. And if it does not, or if you have other questions at the networking sessions, the networking breaks, please follow up with our speakers. One last question while we have just a minute or two. There's a question about how you see the transition of implementation of like actual current HPC, high performance computing knowledge to this quantum ecosystem. And maybe you touched on that in a couple of points, but if you could elaborate a little bit more.
So the point there is you need to, there's a significant gap in how people are approaching HPC solutions and quantum solutions. And I feel like the quantum ecosystem is discovering this more and more. Like you need to kind of walk towards the classical users and help them, like meet them halfway, let's say. And that's why we are now focusing on hybrid approaches where it's easier then to look into the existing HPC solutions and then incorporate those solutions instead of thinking of completely replacing them. This comes from, because technically it's hard to replace the entire pipeline, and operationally we all know how it works in large companies. If you need to change everything, nothing will happen, but if you need to change small things, things will happen. So this is how we think things will be going, and that's why we're focusing on also on these analog approaches where, sure, the devices are not yet the FTQC universal computer that we're all looking for, but they're already providing benefits, and by using them now, we can start, entering the HPC world and convince people that there are ways to start implementing solutions there.